Yo, what's up, Sci Fam? It's your boy Nickel, and today we're going to learn about Newton's second law of motion. So, the way that we're going to structure our note page is first with a title. We're going to title it Newton's second law of motion. We will define it here at the top. We'll talk about acceleration because that's an important vocabulary term to define to understand this law of motion, and then we'll put some examples at the bottom of our page of Newton's second law of motion. So let's begin. Make sure you add that title. So after learning about Newton's first law of motion, we're now going to move on to Newton's second law of motion. And it's the second of three total laws of motion that Isaac Newton is famous for identifying. So the second law of motion states that the acceleration of an object is going to be affected by two things. So the acceleration of an object is affected first by the mass of the object. And second, the acceleration of an object is affected by the amount of force that's applied to the object. So let's think about this for a second. If we have let's just say that we have a soccer ball here, and if I were to try to draw a version of a soccer ball, and we have someone here that's going to come up and kick the soccer ball. And here's their plantar foot, and then they wind this foot way back, and they're getting ready to run up and kick this soccer ball. They're really excited because, yay, they're looking to score a goal. Now let's imagine if they kicked this soccer ball. Let's use an arrow to show that maybe it would go, I don't know, this far, maybe into the goal. So if I were to draw a goal here, they're trying to score a goal. That's a goal. That's at least my best version of it. Okay, well, what if someone came in real quick and replaced this soccer ball with a bowling ball? Ooh. Now, you're probably thinking, ouch, that would hurt. Because just intuitively, as humans and as we've interacted with the world ever since we were young, little, curious babies, we probably understand the fact that if you kick a bowling ball as hard as you kick a soccer ball, this bowling ball, first off, it's not going to go very far. Second is it's probably going to hurt your foot, but we'll talk more about that in Newton's third law of motion. So the bowling ball won't go as far because the mass of that object is much, much heavier than the soccer ball down here is. But if we did want it to go further, what Newton's second law of motion says is that if we change the amount of force, then its acceleration will change as well. So what this person would have to do is they'd have to wind up their foot even further than they did here so that they could kick it harder by providing more force to this bowling ball and get it to go the extra distance. So this is something that we intuitively understand, but Newton put this vocabulary to it, and he also saw that it was something that was a consistent thing, so that's why we call it a law of motion. So the acceleration of an object is affected by how heavy the object is, the mass of the object, as well as the amount of force that's applied to that object. But one of the words that's in here that's really important for us to understand what it means is this word here, acceleration. Is we need to understand what the heck does that mean, that the acceleration of an object is affected. So let's define the vocabulary term acceleration. So perhaps you've driven a car or a go-kart, or you just understand that if you accelerate, it means that you're speeding up, right? Well, that's kind of our background knowledge of what acceleration might mean. But this is just what we typically use the word acceleration for in our everyday language. In physics, however, acceleration is defined a little differently, and it includes that idea of speeding up. But acceleration is defined specifically as a change in either the speed of an object, so like speeding up, or the direction of an object. So, for an example here, if you were to speed up or down, that would be considered acceleration. So when we think about speeding down or decreasing our speed, a lot of times we call that deceleration. But in physics, acceleration is the term that's used for speeding up or slowing down. It's also the term that we use for changing direction. So let's think about this a little bit differently. So if we were to have a human here that is running, I think the most common understanding of acceleration is this idea that when you're running, if you're running ahead and over time you start to run faster and faster and faster, this means that you're speeding up. So the way that I'll draw this, I'll draw some little dots in between this to show that there's more distance traveled over the same amount of time. So therefore this person is obviously speeding up. So here, let's label this one as, over here I'm going to write speeding up equals a type of acceleration. Now let's think about this a little differently. Let's say that somebody's on a skateboard, they kick off the ground and they go whoosh, they move ahead. But then as they keep going, the friction of the wheels on the ground cause them to start losing their speed, and their energy is transferred into that rolling motion and on the ground, and they start to slow down. So at first they get that initial boost and they speed up, but then they begin to slow down. So another type of acceleration is we could say that slowing down also equals acceleration, at least in the terms of physics. And lastly, if we think about this bumblebee right here, if this bumblebee were flying along and was maybe moving in this direction here, let's say it's moving up, but then, whoops, we don't want that. We want to duplicate this image. It changes direction and starts flying down here, and then it starts flying up here, and then it flies over here, and then maybe it does like a little loop-de-loop before it finally ends over here. Let's draw its path. So here's some dots to show that it's changing its direction. Oh, it was going to go over there, but it doesn't. So I got this idea of these different ideas, or these changes of direction, from Khan Academy. So you might recognize these pictures here. But if we have this bee that is changing directions in its flight pattern, then this is another example of acceleration. So I want to kind of explain this in a way that I think might help you understand it. Because acceleration, often, maybe you think of like speeding ahead. Well, if you're driving in the car with your parents and you're going down the highway, you might be traveling at 80 miles an hour going down the highway. But you can sit there and read. You might even fall asleep going 80 miles an hour down the highway because you're going at a constant speed. You're not speeding up. You're not changing your speed, and you're not changing your direction. But if all of a sudden there's a pothole in the middle of the road and your parents had to swerve over to the other lane, you'd probably jerk and look up and be like, oh, what's going on? Because that acceleration, that change in direction gets your attention. Or maybe there was someone next to you, so your parents couldn't swerve to the other lane, and so instead they slammed on the brakes. That is going to also get your attention. And then they speed ahead so that they don't get rear-ended, and that too would get your attention. You'd be able to feel that. So anytime you can feel some change in motion, whether it's because of speed changing or because of the direction changing, that is what we call acceleration. And really, when we think about acceleration is really the fun that we get from roller coasters. Roller coasters are constantly having the speed change, the direction change, and that's really what's fun about it. If you think about in a roller coaster, oftentimes you're not really traveling very fast necessarily. You usually will drive faster getting to the amusement park in your car. But it's those changes in direction as you go up and down and left and right and through the loop-de-loops. That's fun because we have that change in our speed and the change in our direction. And as humans, we can really feel and sense that, and that is usually fun. So as we look at our definition for Newton's second law of motion, the acceleration, either something slowing down or speeding up or changing its direction, is affected by how much its mass is and the amount of force it's applied to it. So these are important terms here now that we understand acceleration a little bit better. So since acceleration is more of just like an addition here to our notes, I want you to actually draw a box around it to show that this is maybe helpful information, but it's not really the definition of Newton's second law. But it does help us understand Newton's second law a little bit better. So I'm just drawing a box around it just to show that, yeah, this is additional information and it is helpful, but this is not part of Newton's second law of motion. It's not part of the definition, at least. The definition is pretty simple. It's just that the acceleration of an object is affected by the mass of the object and the amount of force applied. But below this box, what I'd like to do now is draw some examples of Newton's second law of motion so that we can remember what it is by using some pictures here. So to begin with, let's draw ourselves a free body diagram. So I'm going to draw a box with a dot, and I'm going to draw two of them here so that I can compare two scenarios. So let's imagine here that first off, this object weight is applying a force down on the ground due to its weight, and the force down is 500 newtons, but it's not falling through the floor. So therefore, we need to also provide an equal and opposite force because the ground is holding this object up. And so if it has 500 newtons pushing down on the ground, then that means the ground is pushing up with 500 newtons because this is a balanced free body diagram at this point because this object is not moving. So we'll do that to both of these because we're going to compare the same situation, but with a different variable here. So we have 500 newtons of force up by the ground and down on the ground by this object. Well, let's say that we apply a certain amount of force to this object, and let's just say that this is 1,000 newtons of force. So this object, if we look at this now it's an unbalanced free body diagram, and it would be moving to the, it'd be moving to the right. And if we applied less force, let's say we only applied 750 newtons, then it would also be moving because it'd be an unbalanced free body diagram, but it'd be moving, to the right. And what I'm noticing here is I actually need to delete this arrow because it needs to be larger than my 500 Newton arrows since it's more force. And maybe it'd even help me to draw my 1000 Newton arrow really large. All right. So let's then write and summarize what's in our two pictures here. Is that when we apply more force to an object, remember this object is the same mass in both of these, or if we apply less force, it's going to affect the acceleration or the motion, the changing of direction of this object. So if we apply more force, then we're going to end up having more acceleration. Now imagine if this object was actually moving to the left and we applied the force to the right, then this acceleration would be slowing it down and it would slow down faster. So if we apply more force, we could also slow something down faster, but we could also have it speed up. And the opposite is true. If we apply less force, then we would have, less acceleration. It'd be harder to change that object's direction or its direction or its speed. So more force, more acceleration, less force, less acceleration. Well, let's see what happens if we were to change the mass of our object. So let's use our free body diagram. We will compare it. So we'll draw two of those. This time, let's start by saying that this first one is going to have a force down on the ground of 60 newtons, and it's not falling through the floor. So therefore, the floor is providing an upward force also of 60 newtons. So in this one, we're gonna change the mass of this object. So then if we increase the mass, then this other object is gonna have a stronger force down on the ground. And let's say that this time it's 150 newtons. Let's go with that. Now these arrows have to be equal in size and opposite in direction to show that this is balanced and it's not in motion. So we have two objects here. And if I were to label them, this one has less mass. So let's call this one the baseball. Let's just pretend that's a baseball. And let's pretend this other one has more mass, and this one is going to be a softball. All right, now let's say that someone steps up to bat and they apply a force to both of these. One person applies a force of 80 newtons, let's say, to the baseball. And somebody applies a force of 80 newtons to the softball. Well, based on what we learned about Newton's second law of motion is that even though the same amount of force is applied to the softball and the baseball, one of them will have a better acceleration or a faster acceleration than the other. So if we have less mass, that means it's easier to move. So if we apply the same force to something with more mass, it's going to be harder to move it. So if we have less mass, what we find then is that we end up with more acceleration, meaning that it's easier to change the direction or speed of an object that has less mass. So less mass is going to lead to more acceleration. If something that has more mass and you apply the same amount of force as we did before, it'd be way harder to move it. And so we would say that this has less acceleration. So if two people were trying to hit, well, if one person was trying to hit a baseball and a softball, and they applied the same force to both of them, the softball is not going to travel as far because it is actually a heavier, or it has more mass than a baseball does. So now you know why, if you're ever playing softball, the outfield fence is closer to home plate than it is in baseball. And likely that has a lot to do with the fact that a baseball has less mass and a softball has more mass. The more you know. There you go, ladies and gents. Now you know more about Newton's second law of motion. I'll catch you